our Relativity project. Relativity was a theory devised by Albert Einstein in the early 1900s, and there are two major portions of the theory: special relativity and general relativity. First, we're going to be covering special relativity, which deals with objects that are moving at constant velocities. So now let's say we have a hippie van moving at 90% the speed of light, and it has a flashlight attached to it that's shining out a beam of light moving at the speed of light. Now, intuition would say that according to the person driving the van, the beam of light appears to be moving at 10% of the speed of light. However, Einstein says that this is not the case. Einstein says that the speed of light, even according to the driver, is moving at c, at the speed of light, to any and all observers. So now let's say we have a spaceship that has two mirrors that's bouncing a beam of light up and down on the two mirrors. The person in the spaceship sees it going up and down at c. However, let's say we have a person that's watching the spaceship fly by. He sees the beam of light moving in a zigzag pattern, so therefore the time that it takes to travel upwards is more distance. So how does Einstein say that their measurements can both be right? Easily. Time runs differently. So Einstein says that time is relative, space is relative, however space-time is absolute, and therefore the speed of light is also absolute. So now let's say that all of space-time is a giant loaf of toast. Now let's say that the face of the toast is space, and those two axes are space. Now let's say that the length of the toast is time. So let's divide the toast up into different sections, and let's call each section, I don't know, 1 year. Doesn't matter for this example. Now let's say we have a person that's walking in one direction at 10 miles per hour, or any speed really. Now what will happen is his now slice. Now the now slice is basically your concept of what is happening right now according to you. It's basically angled in a certain direction. So what you think is happening to you right now, to an object millions of light years away, happened millions of years ago. So basically your now slice, whenever you're moving at a constant velocity, is angled. Now this is a very important concept in relativity, is the fact that time is relative, and the fact that your now slice, what you think is happening right now, is really angled. However, we do not notice this here on Earth because the distances are so small and our actual speeds are very small. So now that we understood this, let's move on to general relativity. Now the first concept you have to understand with general relativity is what's called the principle of equivalence. Now the principle of equivalence is that the force that you experience during acceleration and the force that you feel in gravity is the same force. So let's see an example. So let's say we have a plane, and we have a person inside the plane. Now the plane begins to accelerate downwards at, let's say, 2 or 3 Gs. Now what will happen to the person inside it is, as long as this plane is accelerating, he'll be forced upwards onto the roof of the plane. Now Einstein says is that this accelerating force is the same as gravity. So now let's go back in time to Newton. Isaac Newton, when he first discovered his theory of gravity, he first compiled it when he saw that apple fall on his head. Newton would say is that the apple fell downwards, it was pulled downwards by the earth. However, Einstein says is that the rest of the earth rushed up to meet the apple, because everything on earth is accelerating upwards. Well, because acceleration and gravity is the same force, it's the same. So now let's go back to our now slice. So now we know that at a constant velocity, our now slice is angled. However, whenever we accelerate, our now slice is curved. And then Einstein says is that if our now slice is curved, if space-time is curved when we're accelerating, and acceleration and gravity are the same thing, then gravity must be the warping and curving of space-time itself. Yes, everything around us, all of gravity that affects every particle in the universe is just warping and curving of space-time itself. This is probably one of the most important theories and ideas in all of science. In fact, one major branch of science is based off of this idea. So now, let's say that we have a black hole. Now, every object has what's called an escape velocity. Now, escape velocity is basically the velocity, the speed that you need to escape an object's gravity. Now, in the case of a black hole, the escape velocity is larger than the speed of light. So even light, which is moving at c, which is approximately 186,000 miles per second, it cannot escape the black hole because even light is not moving fast enough. So now every black hole has what's called an event horizon. Now the event horizon is basically the edge of the black hole. It's the point of no return. On one side you have the black hole and the singularity, the other side you have freedom. If you go past this event horizon, you cannot go back. You cannot generate an escape velocity fast enough to escape the gravitational pull of a black hole. However, if you do not pass this horizon, you can still escape and you can still live your life out however you choose. So now there are two major pillars of physics. There's general relativity, or just relativity, and then there's also quantum mechanics, quantum theory. Now, the mathematics of these two theories differ greatly, and when you attempt to merge them together to form a grand unified theory, they are not compatible. They do not function. You get answers like 200% and infinity, which do not work in the normal universe. So much of science is dedicated to solving this problem. This science research is what's called quantum gravity, and there are many theories that try to solve this problem, including string theory and loop quantum gravity. So now, I just wanted to say thank you all for putting up with us, thank you for watching, and, yeah, goodbye. No wet birds or expo markers were harmed in the making of this video. Much frustration was carried out through the long process of editing and attempting to upload this video to a flash drive. And while this sounds easy, it really wasn't. So once again, we thank you all for watching and enjoying, and that's all folks. Goodbye.